Yes, your questions first. I would propose to discuss an example. So we have a material. Inside we have this another material. So basically we have two dielectrics with dielectric constants epsilon 1 and epsilon 2. In the absence of both of them, we put a uniform. We didn't discuss this problem, right? Did we? Did we do it all? So let me check. I know I had this in mind. Hmm? Yes. So what else can we discuss? What do you think about? Now we can study the problems involving the materials. Anything you are curious about in electrostatics? What about capacitors?
It depends. Dielectrics materials.
Well, that is about next week. I mean, next week your pre-report is about the forces acting on dielectrics and what happens if you put a dielectric in between a capacitor. So you will basically see that if you put, for example, water in a capacitor, in a vertical capacitor, the water level will rise due to these additional forces acting on the dielectric, etc. So that will be for next week. So after next week, Friday next week, if we still didn't discuss it, you can ask it and we can discuss it in more detail. Let's look at this example. Now we had already studied the problem when we have two conductors at 90 degrees. I mean, it also works if they are at 45 degrees. Now let's do it with dielectrics. So let's say we have some Q charge over here, plus Q. This is a region with dielectric constant epsilon 1. This is a region with dielectric constant epsilon 2. So what is the electric field everywhere? Now with conductors it was kind of easy, at least in region, I mean, let's say this is region 1, this is region 2. In region 2 the electric field was 0, so kind of, it was trivial, let's say. But now things will be a bit more complicated. What would be your suggestion? What shall we try? Just a review. We had looked at this problem of two semi-infinite dielectrics with a charge in one of them. And we had seen that this problem we can still solve with the method of images. In region 2, we have basically two charges, plus Q and some Q prime over here. For if you observe it from region 2. If you observe it from region 1, we had seen that we have a single image charge. Instead of plus Q, we had some Q double prime. And this was kind of, oh, so this allowed us to solve it. So basically the problem is similar to, almost identical to the method of images with conductors, with slight modifications due to these dielectric constants. Now this is our problem. So what would be your suggestion? You can make wild guesses. Just what's your wildest guess about this problem? Make a guess. And if it is wrong, we will learn something. If it is correct, then it will be the boring alternative. We won't learn anything new. So first of all, you should tell me in which region are we considering first? So you see, basically, an observer in region 1 and an observer in region 2, at least in the case of an infinite, semi-infinite dielectrics, they saw different image charges. Region 1, okay. Okay, so here, this is, let me give them names. This is Q2. Q3 and Q4. So we have Q, Q1, Q2, and Q3 for an observer. In region 1. What about region 2?
There should be an image charge on the screen.
Q double prime. For an observer in region 2. So would you like to guess the positions, or shall we try to find the positions? I mean, if we try to find both the charges and the positions, it will become more complicated. So if you have a guess for the positions of these charges, I mean, will they be mirror images? Do you expect them to be mirror images? Not necessarily. So you are saying that these distances so let's say this is D, this is D2. This is D prime, this is D2 prime. And you are saying that D prime and D2 prime and D and D2 in general will be different. Unlike the case with where we had this semi-infinite interface. In that case, it was the same. Here you are thinking that it will be different. Okay. Now, what should we check to see that these are the actual configuration or not? What are the conditions? They are not conductors, by the way. So potential need not be zero. These are dielectrics.
Potential is continuous.
Okay, potential should be continuous. What else?
also continuous.
Is it continuous?
Except on the charges.
Are there charges on the interface?
We are talking interface. On the system or on the interface? We are talking about.
Well, you see, basically, we have to somehow match the potentials in region 1 and region 2. So we need to find some conditions that the potential should satisfy on the interface.
Why should the derivative be continuous?
Derivative of the electric field, you mean?
Yeah.
The normal derivative, you mean? Of the electric field, of the potential.
Should be the same.
Hmm?
The region 2 and the
No, it shouldn't be. Are there charges on the interface?
Not that we know of.
Well, there will be some charges due to the polarization of the medium. So the electric field will not be continuous across the interface. But there is another quantity that will be continuous.
Polarization.
No. What are the equations we have for the dielectric? In a dielectric, what is the curl of E?
0.
It's always 0. And the divergence of what? Is equal to 4 pi rho free. Of the displacement field. Now, we don't have rho free. So, if rho free is equal to 0, it means the component of the displacement field perpendicular to the interface is continuous. And for a linear dielectric at least, D is equal to epsilon times E, minus epsilon times the gradient of phi, of V. So the perpendicular component of the D field is not equal to the normal derivative of V, but the epsilon times the normal derivative of V. Well, since epsilon is not continuous across our interface, so the derivative of the potential, the normal derivative to the surface, also should be discontinuous. So these are the two conditions that we should fix on the boundary. I mean, we should choose the distances d2 and d2 prime and the charges q2, q3, q4, and q prime such that these conditions are satisfied. Now let's choose. Now, what is the potential in region 1? I will give some names. The position of these charges will be R2, R3, R4, and this is R1, this position. This is my origin. This I will choose as my x-axis. This I will choose as my y-axis. So what is the potential in region 1? In this region. This is our region 1. So for an observer in region 1, it will see 4 point charges, Q, Q2, Q3, and Q4. So what is the corresponding potential of? Tell me.
Q1 over 1 minus R1. Q2 minus R2.
This is what then. observer, the potential that an observer will feel in region 1. Is this true? I would feel not. I would say no. Yeah. What is the effect of a dielectric? You see, if we only had a uniform dielectric, these are our equations. If it's uniform. Well, if it is uniform, epsilon is just constant. We can just take it out of that derivative. So it's just like as if there is no dielectric, but the charge is modified by division by epsilon. So we basically have to, if we have an expression for a point charge, which is 1 over charge over r, if we put everything in a uniform dielectric, we just divide by epsilon. Now here we are saying that in region 1, an observer will just see as if the universe is filled with the same dielectric, epsilon 1, but instead of this interface and the effect of this other dielectric, the influence will be just creating these image charges. So in region 1, all of these are divided by epsilon 1. Well, it doesn't really make it too much of a difference, because if it is wrong, eventually we will obtain a Q2, which will be proportional to, let's say, epsilon 1 over epsilon 2. That would tell me that instead of 1 over epsilon 1, I should have 1 over epsilon 2. Now, at least this potential in region 1 satisfies both of our equations. Since we are talking about the potential, and the electric field is the gradient of the potential, curl of the electric field is automatically 0. And the divergence of the electric field in region 1 is just a single Dirac delta in the position of my charge. So that is my free charge density. So at least this solution satisfies my equations in region 1. I don't know whether it satisfies the boundary condition. Those are the things that I should check. Now, what about the potential in region 2? What should I say? R1, the position of this charge is R1. So we said that Q double prime will be basically there. Now again, this potential satisfies all my differential equations. And well, furthermore, my potential satisfies the boundary conditions at infinities. At infinity, the potential should go to 0. The only thing that we have to check is whether these solutions, these proposals satisfy the boundary condition at my interface. Now let's look at let's say this point. Let's call that position Rx. So we need to have V1 at the position Rx should be equal to V2 at the position Rx. Well, if D and D2 are different, R1 minus Rx is equal to R2 minus Rx Now let's see. Let me just first write it down. What I need to have is 1 over epsilon 1, 1 over Rx minus R1, plus 1 over epsilon 1, 1 over Rx minus R2, plus 1 over epsilon 1. Now these are Q1. This is Q, Q2, Q3 over Rx minus R3, plus 1 over epsilon 1, Q4 over Rx minus R4. This should be equal to 1 over epsilon 2, Q double prime over R minus Rx. Now Rx minus R1. This is one condition we have. And if we take, how do you propose to proceed now? Well, let's try. Let's expand a bit. So Rx is, let's say, its magnitude in the x direction, with its component larger than 0. And what we have, R1, is, let's say, x0 in the x direction plus y0 in the y direction. Or, now what we use, d and d prime. This is d prime, this is d, this is R1. R2 is d prime in the x direction minus d2 in the y direction. R3 is minus d2 prime in the x direction minus d2 in the y direction. And R4 minus d2 prime in the x direction plus d in the y direction. So let's see, Rx minus R1. What is Rx minus R1?
Rx minus d squared plus d squared.
Rx minus d prime squared plus d squared under square root. Rx minus R2. Rx minus R3. Rx minus R4.
Rx plus d prime squared plus d squared.
So let's see, 1 over epsilon 1. Q over Rx minus d prime squared plus d squared 1/2 plus 1 over epsilon 2 Q2 over Rx minus d prime squared plus d2 squared to 1/2 plus 1 over epsilon 1 Q3 over Rx plus d2 prime squared plus d2 squared 1/2 plus 1 over epsilon 1 Q4 over Rx plus D2 prime squared plus D squared. This should be equal to Q double prime 1 over epsilon 2 Q double prime over Rx minus D prime squared plus D squared. And this should be true for all Rx larger than 0. How can we satisfy this equation? You are free to make wild guesses. Sum of all the charges. Well, that definitely will not work. You see, since this is true for all values of Rx, the functional forms of both sides should also match. Because if the functional forms do not match, you can make them equal at a given point, but it will not be equal at a different point. So to make the functional forms match, you see the first term on the left-hand side and the first term on the right-hand side, they have the same functional form already. Well, the second term on the left-hand side doesn't have exactly the same functional form, but we can make them have the same functional form if we assume that D is equal to D2. So if this is the case, then the first and the second terms have the same, on the left-hand side have the same functional form as the term on the right-hand side. Now the third and the fourth terms on the left-hand side cannot have the same functional form as the term on the right-hand side. Because you see, if you just look at the functional forms, on the right-hand side we have Rx minus some positive number squared under the square root. But the third and the fourth terms are Rx plus some number squared under the square root. Since they cannot have the same functional form, my guess would be that their sum should be 0.
D and D prime or D2 and D2 prime should be positive always. They should be positive.
Well, that is how we define them. D2 and D2 prime and D prime, those are the distances. And since they are distances, I mean, whether they are on the negative x-axis, positive x-axis, negative y-axis, positive y-axis, we took care of that with the choices in these position vectors. So that basically, I mean, so you see the third term and the fourth term, since D2 and D2 prime, D and D2 prime, D and D2 are equal, the third and the fourth term, they have exactly the same functional form, which is different than the term on the right-hand side. Since they have the same functional form, we can make sure that they cancel each other. So that tells me that Q3 plus Q4 should be equal to 0. You see how many parameters we had in our problem to start with? We don't know Q2, we don't know Q3, we don't know Q4, we don't know Q double prime, we don't know D2, we don't know D2 prime. So we have 6 parameters in our problem which we need to determine. Now, if these are satisfied, we still need to have Q plus Q2 times 1 over epsilon 1 should be equal to Q double prime over epsilon 2. So we have 6 parameters to determine. Now we have 3 equations. If these 3 equations are satisfied, I satisfy all the boundary conditions on this horizontal plane, semi-infinite plane. And hopefully, by imposing additional 3 constraints, I will be able to satisfy all my boundary conditions on the vertical plane also. That's the hope. So let's see if it works. So these 3 make sure that I satisfy the continuity of the potential. I didn't yet look at the derivative. But these 3 equations make sure that my potential is continuous across the horizontal interface. Well, I have 3 more boundary conditions to satisfy. And the hope is these 3 more boundary conditions will give me 3 more equations, and that should be enough. I mean, if they, for example, give me 5 more constraints, then I would have 8 conditions that 6 equations should satisfy, and in general, I cannot get a solution. That will tell me that this configuration of images is not the solution. In that case, we have to do some other tricks. Now, hopefully, we will not need that, but let's continue. Let's look at the continuity of the potential in the vertical side. Let's just choose, this is our y. I will still need these. And ry, this is an arbitrary point on the vertical plane, is its component in the y-hat direction. Now we have to write the potentials and equate the two. 1 over, well, let's first write r1 minus ry. Distance is equal to d prime squared plus d minus ry squared under square root r2 minus ry plus d2 plus ry squared and r3 minus ry and r4 minus ry. Now let's write the potentials. 1 over epsilon 1 q over r minus r1 minus ry. This is d prime squared plus d minus ry squared under square root plus 1 over epsilon 1 q2 over d prime squared plus d2 plus ry squared under the square root plus 1 over epsilon 1 q3 over d2 prime squared plus d2 plus ry squared under the square root plus 1 over epsilon 2 epsilon 1 over epsilon 1 q4 over d2 prime squared plus d minus ry squared under the square root. This should be equal to 1 over epsilon 2 q double prime divided by d prime squared plus d minus ry squared under the square root. Now, this time the first and the fourth term on the left-hand side Well, the first term has the same form as the first term on the left-hand side has the same functional form as the term on the right-hand side. The fourth term can also be brought in the same form, assuming that d prime is equal to d2 prime. And if this is satisfied, then q over epsilon 1, q plus q4, 1 over epsilon 1 times q plus q4 should be equal to 1 over epsilon 2 times q double prime. And the other two terms I can still, they are already in the same form. Well, did I make a mistake somewhere? R3 is, okay, no. Well, the second and the third terms on the left-hand side, they will be in the same form if d prime is equal to d2 prime, but we already assumed that. So they are already in the same form, and what remains is q2 plus q3 should be equal to 0. So these are the new conditions we have. Well, we had the previous conditions. So let's try to simplify them a bit. So what do we have? D prime is equal to D2 prime, and D is equal to D2. So this basically tells me just as if in the conductor case, the image points are at the symmetrical points. They should be at the symmetrical points. So this is this equation and this equation. And then we have Q2 plus Q3 is equal to 0. This is this equation. And Q2 is, if you just combine this with this equation, Q2 is equal to Q4. So this is this equation we have. And if Q2 is equal to Q4, the equation here and the equation here, they are the same equations. And we have 1 over epsilon 1 q plus q4 is equal to 1 over epsilon 2 q double prime. So we have 1, 2, 3, 4, 5 equations. We have 6 unknowns, or 7. We don't know 4 charges. We don't know. Said we didn't know 2 distances. So we had 6 unknowns. Now we have 5 equations. So we are still missing at least 1 equation. Well, we have 2 boundary conditions more that we need to satisfy. So the risk would be we might be having too many too many constraints. Well, let's see. Well, just to simplify things a bit, let's just put the first 4 of these equations into our expressions. So V1 in region 1 will be 1 over epsilon 1 q over r minus r1 plus 1 over epsilon 2 or minus 1 over epsilon 2 q3 over r minus r2, because we know that q2 is minus q3, plus 1 over epsilon 1 q3 over r minus r3, and q4 is just q2, which is minus q3, minus 1 over epsilon 1 q3 over r minus r4. And the potential in region 2 will be 1 over, well, we said that it was 1 over epsilon 2 q double prime divided by r minus r1, But you see q double prime over epsilon 2 is nothing but q plus q4 divided by epsilon 1, but q4 is minus q3. So this is equal to 1 over epsilon 1 q minus q3 divided by r minus r1. Well, I will also need the distances. I will just remove the 2 because we know that d is equal to d2, d prime is equal to d2 prime. Now, to take the derivative, we need to find the expression of the potentials at an arbitrary point. Then take the derivative and then go to the boundary. So we cannot just set the r point to be on the boundary and claim to be able to take the derivative. So we have to write the potential at an arbitrary point r. Let's say this is x in the x hat plus y in the y hat. So r minus r1. This should be equal to x minus d prime r minus r2 plus d squared r minus r3 to the power 1/2. So let's start with V2. This is equal to 1 over epsilon 1 q minus q3 over r minus r1 to the power 1/2. V1 1 over epsilon 1 q over r minus r1 to the power 1/2, and then minus q3 over epsilon 1 x minus d prime squared plus y plus d squared plus, well, the third term, 1 over epsilon 1 q3 and minus 1 over epsilon 1 q3 over r minus r4. This is 4. Okay, so these are the potentials at an arbitrary point. Now we need to take their derivatives. So we need to have epsilon 1 del V1 over del, what's the normal direction? On on the horizontal plane. That's the y direction. This should be equal to epsilon 2 times del V2 by del y in the r is equal to rx, and epsilon 1 del v1 over del, well, this is on the horizontal plane. What is the normal direction to the surface? It's the x. Here we have the vertical, this is the x-axis. Well, you can choose any direction you want, in fact. Either the plus x or minus x doesn't really make any difference. Del x should be equal to epsilon 2, del v 1 over del y, del x, sorry, at r is equal to ry. Well, instead of r is equal to rx, let's say y is equal to 0. And this is at x is equal to 0. Well, this is in fact why I just wrote the potentials at an arbitrary point, because you cannot just set x is equal to 0 and take the derivative with respect to x. So let's see, let's start with the first one. So we have epsilon 2 del v2 by del y when y is equal to 0. This is equal to epsilon 2 del over del y. This is our v2. Evaluated at y is equal to 0. So this is equal to epsilon 2 over epsilon 1, q minus q3. Well, if you take the derivative with respect to y, you would get minus y minus d divided by x minus d prime squared plus y minus d squared, all to the 3/2. Of course, you have to set y is equal to 0. So epsilon 2 times del v2 by del y, evaluated at y is equal to 0, is minus epsilon 2 over epsilon 1, q minus q3, d over x minus d prime squared plus d squared. So this is one of the derivatives we need.
Why minus?
Hmm?
Why minus?
This minus over here.
So D has minus sign.
Hmm?
So D has also minus sign, not D minus D.
But that's squared. Minus d squared. I mean, why do we have this minus sign? You see the... Hmm?
This,
Hmm?
yeah, just cancels. And y equals 0. So I can plus D.
Oh, you are right, you are right. So it's plus d. Because I'm setting y is equal to 0, that is minus minus d, that is plus d. Or I should put minus here and minus d over here. Let's continue with the first term, epsilon 1 this time. Well, this is our v1. Well, I will not write each step explicitly. Eventually, we will be putting y is equal to 0. So this is equal to epsilon. Well, epsilon 1s will cancel. We don't have any epsilon 1s anymore. And if you take the derivatives, you would end up having q times d over x minus d prime squared plus d squared under the cube 3/2 plus q3 times d over x minus d prime squared plus d squared plus q3d, no, minus q3d over x plus d prime squared plus d squared and plus q3d over x plus d prime squared plus d squared 3/2. Do you agree? So we have some cancellations already. So the third term and the fourth term, they basically cancel each other. So the condition we have now is epsilon 2 over epsilon 1, q minus q3, d over x minus d prime squared plus d squared to the power 3/2. This should be equal to, well, what we are left with is q plus q3 d over the same factor 3/2. So now we have our sixth equation. So epsilon 2 over epsilon 1, q minus q3 should be equal to q plus q3. So this tells me that, let's say, epsilon 2 over epsilon 1 times q minus q should be equal to epsilon 2 minus epsilon 1 q3 plus q3, or q3 should be equal to epsilon 2 minus epsilon 1 over epsilon 2 plus epsilon 1 q. So now we have all the unknowns. Well, the other charges, we know q3. Well, this q2 should be equal to minus q3 minus epsilon 2 minus epsilon 1, epsilon 2 plus epsilon 1 q. q4 is equal to q2, which is minus epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 times q. Now we know all the unknowns, but still we have to check that there's one more boundary condition we didn't check yet. Does this satisfy that boundary condition? You see, what up to now we check the continuity along the x, continuity of the potential along the x, continuity of the potential along the plane in the vertical plane, continuity of the epsilon times the derivative of the potential in the horizontal, but we didn't check the continuity of epsilon times the derivative of the potential in the vertical. That's still something we have to check. And well, let me not check it here. It will be satisfied. So now we know our solutions. So we had, this was our epsilon 1, this was epsilon 2. Oh, by the way, q double prime. Q double prime is epsilon 2 over epsilon 1. Q double prime is equal to epsilon 2 over epsilon 1 q plus q double prime. Q plus q prime. Q4. Well, let's check. Q plus q4. And q4 is q2. Now q4 we have over there. This is equal to epsilon 2 over epsilon 1 q plus q in q parentheses 1 minus epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1, which is epsilon 2 over epsilon 1 q twice epsilon 1 divided by epsilon 2 minus epsilon 1. Epsilon 1's cancel. We have twice epsilon 2 over epsilon 2 minus epsilon 1 times q. So we have the Q charge. Here we have Q2, which is minus epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 Q. But keep in mind, this is the image charge that an observer in region 1 will see. This distance is the same as this distance. Here we have an image charge, which is again minus epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 Q. This distance is the same as this one. And we have this charge over here, which is epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 Q. And so here we have Q double prime. Q double prime is the charge that an observer in region 2 sees. It doesn't see Q, it doesn't see Q1, it doesn't see Q2, it doesn't see Q3, neither Q4. It only sees Q double prime. And this Q double prime is twice epsilon 2, this is plus, over epsilon 2 plus epsilon 1. Now we can check several limits. And well, if there is no two dielectrics, if it's a homogeneous dielectric, you see in region 1, you don't see any of these image charges. Well, that is expected. There is no charge anywhere. There is no interface to create those image charges if epsilon 1 is equal to epsilon 2. And then the only thing you see is that the charge Q, no images. And if you are in region 2, you will only see Q double prime, which if epsilon 1 is equal to epsilon 2 is again Q. And whether you are in region 1 or in region 2, the only thing you see is a point charge of charge Q. So at least that checks. Another limit is we can consider the limit of a conductor in region 2. Well, the conductor limit is you just take epsilon to infinity. If epsilon is infinite, that is epsilon 2 is infinite, you see you have the plus Q charge. Its first image is minus Q. Its below image here, this becomes minus 2 due to the horizontal plate. This becomes minus Q. And this diagonal limit just becomes plus Q. That is what we had used when we were looking at two conductors at 90 degrees. And for an observer in region 2, if epsilon 2 goes to infinity, well, it seems that it sees a charge of 2Q, but keep in mind the potential is 1 over epsilon 2 times 2Q, etc. But epsilon 2 goes to infinity, so the potential is 0. So no electric field whatsoever. It won't see anything. So at least in the limits that we know, it works. Now,
when we are solving a problem like this, is it good to assume as many assumptions as we can or minimize our assumptions?
Well, you see, as you see, the computations are quite long. So if you make assumptions, you will minimize your work. But of course, if you make too many assumptions or if you make assumptions that are not wrong, you might not be able to find the solution. So it's kind of an interplay. What I would do is just make as many assumptions as make sense. If I find the solution, then the uniqueness theorem tells me that that is the solution. I didn't lose anything. For example, I would have just said that those distances are equal from the start. So that would have simplified my life at the beginning. Not much, but a bit. It saves time. But of course, it could have turned out that I won't be able to find the solution with that assumption. In that case, I have to go back, start over, and not make assumptions. Even the saying that I have 3 image charges is an assumption to start with. And it might be that it doesn't work. But it did turn out to work. So since it does work, I'm saved. The uniqueness theorem tells me that it is the unique solution. I don't need to worry. Now, let's look at a couple of cases. So what happens when, let's say, if epsilon 2 is larger than epsilon 1. Well, it's almost a conductor, not exactly a conductor. You see, we have this image charge over here. Here we have a charge which we called Q4, which is, let's say this is a positive charge, this is less than 0, it's a negative charge. You see, epsilon 2 is larger than epsilon 1, so epsilon 2 minus epsilon 1 is positive, but we have this overall minus sign, which makes it negative. And here we would have a Q2 charge, which is less than 0. And here we would have the Q3 image charge, which will be kind of larger than 0. So if you would plot the electric field lines, just sketch it, let's say. Well, they will be kind of bending in this direction because there's a negative charge over there. Well, when it reaches the interface, remember on the other side of the interface, the electric field is the electric field of a single point charge. There are no image charges on the other side. So the electric field lines will be uniform. Will be radial. And similarly, the electric field line, this one will kind of bend like this. And then radial beyond that point. This electric field line will bend like this. You see there's this plus charge. That plus charge is kind of pushing the electric field lines away. Furthermore, there are the minus charges. They will be pulling the electric field lines towards themselves, causing the electric field lines to bend. And again, when it crosses the interface, it will be just radially out. Well, I don't think these field lines will be straight, but more or less straight. Well, this is more or less how the electric field lines will look like in this case. Now, the other case is, probably a bit more funny. You see what happens in the other case. Epsilon 2 is less than epsilon 1. You see, if epsilon 2 is less than epsilon 1, epsilon 2 minus epsilon 1 is negative. If epsilon 2 minus epsilon 1 is negative, the image charge over here will be positive, not negative. So we have a test charge over here. The charge, this plus Q, this will be Q4, which is larger than 0. Here we have Q2, larger than 0. Here we have Q3, less than 0. So the electric field lines will be something like this. This is how they will look like. Well, this epsilon 2 larger than epsilon 1 tells me that the region 2 is more polarizable than region 1. If you think of why this happens, well, just consider the dipoles at the interface. So you have one dipole in region 2. Next to it, you have another dipole in region 1. Both dipoles have their negative sides pointing toward the positive charge, and positive charges away from our positive charge. On the interface, we have the positive side of the dipole in region 1. In region 2, we have the negative and also the negative side of the dipole in region 2. Now, if region 2 is more polarizable, or if region 1 is more polarizable, then the positive side of the dipole in region 1 is more positive than the negative side of the dipole in region 2. So overall, in that region, I would expect a positive charge to accumulate in that region. So that's why the interface behaves like a plane with positive charge and pushing away the electric field lines. Well, it will be positive. All the interface will be effectively positively charged. Not just the closest points, even the corner will be effectively positively charged, but the positive charge at the corner will be weaker than the points closer to my plus Q charge. So this will be more positive charge just here and more positive charges here. So they will basically bend the electric field lines towards the corner.
What about the other case?
In the other case, again, the idea is basically the same. So you have these two dipoles adjacent. Yep. Now, epsilon 2 is more polarizable. So the negative charge of the dipole in region 2 is more negative than the positive size of the dipole in region 1. So the interface is effectively negatively charged. So there are many negative charges here, many negative charges here, well, some negative charges also here. So this is basically how it will look like. So what is the charge density on the interface? The bound charge. There are no free charges. The only free charge is the point charge we put. But what about the bound charges? How can we determine the bound charges?
You know the electric field at interface.
How? We know the potential. From the potential, we can calculate the electric field at the interface and
We count the charge density.
by.
2.
Okay, we know the electric field at the interface on both sides of the interface. How can we use that to determine the potential, the charge density?
Isn't the electric field continuous?
Is it continuous?
The surface charge is not.
If there is a surface charge, it is not continuous. So that is basically how we can determine it, calculate the discontinuity of the electric field. That will give you the charges on the surface. So let's see. We already had calculated the derivatives. So we need these two derivatives. Let's just calculate it in the horizontal plane. So this is one derivative we have. Let me divide by epsilon 2. Well, this is the y component of the electric field in region 2 in the horizontal plane.
This is only the normal direction.
Yes, there was this criticism. This is only the normal direction. Is the problem? Well, the horizontal component of the electric field has to be continuous. It's only the normal direction that it can be discontinuous. Because you see, the curl of the electric field is always zero, whether we are in medium or not. This tells you that the component of the electric field parallel to any surface is continuous. So we don't need to worry about the parallel component. It will be continuous, so we cannot relate it to the charge density. But the divergence of D is equal to 4 pi rho B, 4 is equal to 4 pi rho B plus rho. This equation tells me that the perpendicular component of the electric field, the component perpendicular to the surface, is discontinuous, and this discontinuity is 4 pi sigma plus sigma B. Sigma, I mean sigma free. In this problem, sigma free is 0. There's no charges on the surface. We didn't put any charges there. It's only rho B. So if you just look at the discontinuity in the electric field, that will tell me what the bound surface charge density is. Now, of course, I have to define what this discontinuity is. Is it the electric field below the plane minus the above plane, or above the plane minus the below the plane, and what is above and what is below the plane? So in general, what we do is the electric field outside minus the electric field inside is equal to 4 pi sigma n. And n is a unit vector pointing from below the surface, from inside the surface, to the outside. So this is how we define the inside and the outside. So if this is our surface, if we choose z-axis as our n direction, so outside is region 1, inside is region 2, and n is z. So we already know the derivatives of the potential, or the perpendicular components of the electric field. So 1 over epsilon 1 q plus q3 divided by x plus d, x minus d prime squared plus d squared 3/2. This is the electric field, the perpendicular component of the electric field in region 1, which we identified as the outside. Well, minus this one is the electric field, minus 1 over epsilon 1 q minus q3 divided by x minus d prime squared plus d squared to the 3/2. This should be equal to minus 4 pi sigma. Well, minus, because these terms are the derivatives of the potential, the electric field is minus the derivatives. And if you just combine the two, let's see, q terms, they just cancel. And we end up having 2 over epsilon 1, 2q3 over epsilon 1, 1 over x minus d prime squared plus d squared to the 3/2. This is equal to minus 4 pi sigma. And Q3 was equal to epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1. Q. So sigma is equal to minus 1 over 2 pi epsilon 1 epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 Q 1 over x minus d prime squared plus d squared raised to the power 3/2. So let's check if we had made any sign mistakes or not. Now one thing, if epsilon 1 is equal to epsilon 2, there shouldn't be any surface charge density because there's no interface. And if epsilon 1 is equal to epsilon 2, yes, it satisfies. Now we said that if epsilon 2 is less than epsilon 1, the surface charge density is positive. Let's see, if epsilon 2 is less than epsilon 1, then the term in parentheses is negative. We have an overall minus sign, so the surface charge density is positive. And if the epsilon 2 minus epsilon 1 has the other sign, the surface charge density has the other sign also. So at least we made what's called the sanity check. Our results make sense, at least in certain limits. Whether it is correct or not is another problem, is another issue, but at least it makes sense. And furthermore, we would expect the largest charge density to be straight below the charge at this point. That's where we expect the largest charge density. But that is the point when x is equal to d prime. Well, if you look at our expression is largest when x is equal to d prime. And as you go away from x is equal to d prime, it just gets smaller and smaller.
If epsilon 2 is smaller than epsilon 1, it turns out to be minus.
Okay, so if epsilon 2 is less than epsilon 1, that's what you are saying, right?
Much less than.
Well, as long as if we are only looking at the signs, if epsilon 2 is less than epsilon 1, then it is that parenthesis is negative and sigma is positive.
Much less than 1, then parenthesis is positive.
No. If epsilon 2 goes to 0, then the parenthesis is minus epsilon 1 over epsilon 1, which is minus 1. As long as epsilon 2 is less than epsilon 1, whether by a very small amount or by a very large amount, that parenthesis is negative. It only changes sign when epsilon 2 is equal to epsilon 1, with the constraint that both are positive numbers.
Sort of an off-topic question. If we go back to this, if we said that, for example, Q3 is epsilon 2 minus epsilon 1 over epsilon 2 plus epsilon 1, which is this value, right?
Well, it depends on the magnitudes of epsilon 1 and epsilon 2. It can be positive or negative. If epsilon 2 is larger than epsilon 1, then that Q3 is positive. If epsilon 2 is smaller than epsilon 1, then Q3 is negative.
And it can be a rational function, right?
Sure.
So
It can be, in fact, any number less than any number multiplying Q.
if we have, for example, for Q, if we have an electron,
Okay.
then we cannot express Q as a rational function times charge.
You see, these image charges are not real charges. Okay, there are two issues. One is these image charges are not real charges. So in principle, they can have any charge, even fractional charges. No problem with that. Second issue is, well, we are considering continuous media. we don't really have discrete charges. But within this description, everything is continuous, every value of charge is possible. So we are not really looking at the quanta of charge. But even in that case, since these things are not the real thing, they are effective charges, let's say, they can be fractional. No problem with that. Well, the tricks that we are using, whether we have medium or not, is basically the same. I mean, up to now, the method we use almost all the time is method of images or separation of variables. Just find some candidate solution and then make sure that your candidate solutions satisfy your boundary conditions. That's practically what we are always doing. And as long as your candidate solution satisfies your boundary conditions, you are safe. That is the solution. Of course, your candidate solution should satisfy these two equations. The second one always tells us that E is equal to minus the gradient of phi. And then the first one, assuming we have a linear medium, then D is equal to epsilon times E, which is minus epsilon times the gradient of phi. Divergence of epsilon times the gradient of phi should be equal to 4 pi rho, minus 4 pi rho free. By rho free, we mean the charge density corresponding to free charges, the charges that we put that we are controlling. I didn't take epsilon out on purpose because it need not be constant. We had seen many examples where this basically takes two discrete values in different regions.
Well, we said rho free is equal to 0, then in region 1 and region 2, the charge densities are the same.
I mean, rho free is equal to 0 in our problem, but we didn't say the charge rho bound. I mean, what do you mean by charge density? You see, rho, the total charge density will be rho free plus rho bound. Rho free can be 0, but that doesn't mean rho bound has to be 0. Well, in our problem, in region 1 and region 2, epsilon is constant. Rho free is 0 in region 1 and region 2. Inside our regions. If this is satisfied, then Laplacian of phi, this is equal to 0, or divergence of E is equal to 0. Again, I repeat, this is true inside our regions, not on the boundary. But this tells me that rho is equal to 0. Since rho free is 0, rho is also 0, rho bound is 0. Well, rho bound, remember, is equal to minus the divergence of our polarization. So basically we have the polarization is divergenceless. We have 0 charge, whether bound or free, inside our region. But we had just seen that the surface charge density this is sigma b, is not necessarily 0. There is an effective surface charge due to the different polarizability of the two medium. Inside the medium, since we have homogeneous polarizability, these these induced dipoles, or these dipoles, the positive and negative sides, they exactly cancel each other. But on the interface, since both sides of the interface have different polarizabilities, the dipoles on the surface of this interface, they cannot cancel each other, and hence we have a net surface charge density on this interface. Any questions? So let's end the lecture now. Again, the exam will be not this weekend, but the following weekend. And next weekend, we will be studying the work and energy in dielectrics and the forces acting on dielectrics. That is also part of the exam. And after the exam, we will start magnetic fields.